buckle up, because today we're diving headfirst into some seriously mind-boggling stuff, black holes. You've given us quite the reading list for this deep dive. A brief history of black holes, a crack in everything. Even dipping into the heavy stuff like modern general relativity. You're clearly serious about unraveling these cosmic mysteries.
It's an intriguing journey for sure. And these sources offer some incredible insights. It's not just about the black holes themselves, but the brilliant minds who helped us understand them.
Right? It's like a detective story across time and space. So where else could we possibly begin but with the one and only Albert Einstein?
Before Einstein, our understanding of gravity was, well, a little flat. Isaac Newton gave us the basics, and for centuries that worked well enough. It's like using a regular map to get around helpful, but it doesn't show you the mountains or valleys.
Then Einstein comes along with his general theory of relativity and turns everything upside down. Suddenly, gravity isn't just a force. It's about how massive objects actually work the fabric of space-time. That's where the bowling ball on a trampoline analogy comes in handy, right?
Yeah. Exactly. Imagine that bowling ball making a dip in the trampoline. That's essentially what massive objects do to space-time. Now picture an object so heavy, so dense, that it makes a bottomless pit in that trampoline. That's a black hole. Even light, the fastest thing in the universe, can't escape that gravitational well.
Okay, that's already blown my mind, and we're just getting started. But hold on. If gravity is warping space-time everywhere, how did Einstein prove his theory was more accurate than Newton's?
That's where the planet Mercury comes into play. Astronomers had noticed its orbit was a bit off. It wobbled in a way Newton's equations couldn't quite explain. But Einstein, his theory predicted that wobble with incredible accuracy. It was a major win for general relativity and revolutionized our understanding of the cosmos.
Okay, so Einstein gave us the framework, but then things got even more interesting. You included an excerpt about Subrahmanyan Chandrasekhar, a young astrophysicist who uncovered something called the Chandrasekhar limit. What's that all about?
Chandrasekhar was brilliant. He was fascinated by what happens to stars when they die. And he figured out that when a star runs out of fuel, it doesn't just fade away. It can become a white dwarf. Think of it like a dense, Earth-sized ember left over from a bonfire.
Makes sense.
Yeah.
But there's a limit, right? That's where Chandrasekhar's discovery comes in.
Exactly. He calculated that if a star is massive enough, we're talking significantly larger than our sun, it can't become a white dwarf. It collapses under its own gravity into something far denser.
Okay, so what happens then? It just keeps collapsing.
That's the question that shook the world of astrophysics. You have to remember, this was a radical idea at the time.
Oh.
Arthur Eddington, one of the leading astronomers of the day, vehemently opposed Chandrasekhar's theory.
Wait, really? Why? It seems like a logical conclusion.
Science isn't always about logic. It's about challenging established ideas. Eddington believed there had to be some unknown law of physics preventing a star from collapsing into something so extreme. It took decades for the scientific community to fully accept Chandrasekhar's findings.
Wow. Talk about a scientific showdown. So while this debate was raging, another player enters the scene. And this one isn't even an astronomer. We're talking about Karl Schwarzschild, right? A lieutenant in the German army during World War I.
And what a story. Imagine being in the trenches of World War I, surrounded by chaos. And instead of focusing on the battle, your mind is lost in the complexities of Einstein's equations. That was Schwarzschild.
Dedication to the nth degree. So what did he figure out amidst all that?
Schwarzschild found a solution to Einstein's equations that described the incredibly intense gravity around a perfectly spherical, non-rotating object. It was the first theoretical description of a black hole, and he did it from the front lines of a war.
Wow. So here we have Schwarzschild in the trenches, laying the groundwork for one of the most mind-blowing concepts in astrophysics.
Right.
What a story.
Sadly, Schwarzschild died just months after his discovery, never fully realizing the monumental impact of his work. But his solution, born in such an unlikely place, would change our understanding of the universe forever.
It's incredible to think that while the world was embroiled in war, these scientific discoveries were happening, pushing the boundaries of what we knew about the universe. Speaking of pushing boundaries, you mentioned quasars earlier. Let's dive into those next, because those sound absolutely wild. You mentioned quasars earlier. Let's dive into those next, because those sound absolutely wild.
Imagine a cosmic lighthouse, but instead of guiding ships, it's shining brighter than entire galaxies. From billions of light years away. That's a quasar.
Okay, that's just showing off. How can something be that bright from so incredibly far away?
That was the million-dollar question when astronomers first stumbled upon these objects. They saw these incredibly bright points of light, but they were so far away. The energy they were emitting was mind-boggling.
So what's the answer? What could possibly power something that luminous across such vast distances?
The only explanation that made sense, and it's a doozy, is a supermassive black hole, billions of times heavier than our sun, devouring matter and releasing an insane amount of energy in the process.
Hold on, I thought black holes were, black. How can something that pulls everything in even light be shining so brightly?
That's the amazing part. It's not the black hole itself that's glowing, but the superheated matter swirling around it. Picture it like this. As gas and dust get pulled toward the black hole, they spiral around it, forming a disk. And this disk gets incredibly hot due to friction and intense gravitational forces.
Hmm.
That what emits all that light we see from billions of light years away.
Wow, so it's like a giant cosmic whirlpool of superheated matter lit up by the sheer power of a black hole. That's incredible.
And remember how we talked about radio astronomy earlier? Quasars were initially discovered through radio telescopes because they emit incredibly strong radio waves. It was like a hidden universe suddenly came into focus.
So we went from thinking black holes were these invisible, silent monsters lurking in the darkness to realizing they could power the brightest objects in the universe.
Exactly. And it doesn't stop there. Speaking of mind-blowing discoveries, we have to talk about Stephen Hawking and his groundbreaking work on something called Hawking radiation.
Okay, I've got to hear Hawking radiation. What's that all about?
This is where things get really weird, even by black hole standards. We've talked about how nothing, not even light, can escape a black hole once it crosses the event horizon, right?
Right. That's kind of their whole deal, a one-way ticket to oblivion.
That's what everyone thought.
Mm.
But Hawking brought quantum mechanics into the mix, and he found that black holes aren't entirely black after all.
Okay, you've officially piqued my curiosity.
Eh.
How can something that traps even light emit anything? What's this quantum mechanics twist?
It all comes down to this concept in quantum mechanics called virtual particles. These particles are constantly popping in and out of existence, even in the vacuum of space. They're like tiny, fleeting pairs of matter and antimatter particles that appear and then annihilate each other almost instantly.
So how does this relate to a black hole?
Well, imagine a pair of these virtual particles popping into existence right at the edge of a black hole's event horizon. One particle gets sucked in, while the other escapes before it can be annihilated.
And that escaping particle is what we call Hawking radiation.
Exactly. It's like the black hole is slowly emitting particles, losing a tiny bit of mass and energy over time.
So you're telling me that even these cosmic behemoths, these seemingly unstoppable forces of nature, aren't invincible. They eventually evaporate.
That's the mind-bending implication of Hawking radiation over incredibly long periods, like trillions upon trillions of years. Black holes can actually shrink and eventually disappear entirely.
That's wild. But if black holes are constantly gobbling up stuff, including light, which carries information, wouldn't that mean information is being destroyed?
That's a great question, and it leads us to one of the biggest unsolved mysteries in physics, the black hole information paradox. We'll dive into that right after a quick break.
So before the break, we were talking about black holes slowly evaporating and this whole information paradox, like the universe's biggest cosmic delete button. But something about that doesn't quite sit right.
It's one of the most tantalizing puzzles in physics because it pits two fundamental theories against each other: general relativity, which governs the very large, and quantum mechanics, which governs the very...
And I'm guessing those two don't always play nicely together.
You got it. Quantum mechanics says that information can never be truly destroyed. It might change form, get scrambled up, but it's always conserved somewhere in the universe. But then black holes come along and seem to break that rule.
So on the one hand, we have these black holes swallowing information whole, and on the other, we have quantum mechanics saying, hold on, information can't just disappear like that. So where does that leave us?
That's the paradox. It's like trying to fit a square peg into a round hole. Physicists are still grappling with this, trying to figure out how to reconcile these two seemingly contradictory ideas. Some believe that information might be encoded in subtle ways in the Hawking radiation itself. Others propose that maybe black holes don't completely destroy information, but somehow preserve it like a cosmic library, even after they evaporate.
So the jury is still out on this one. It's kind of mind-blowing to think that something as fundamental as information conservation could be challenged by these cosmic giants.
That's the beauty of science. It keeps us asking questions, pushing the boundaries of what we think we know. Every answer often leads to more questions, deeper mysteries to explore.
Speaking of exploration, how do we even study black holes if they're invisible? It's not like we can just point a telescope at them and call it a day.
You're right. Directly observing a black hole is impossible. At least with our current technology, they're literally invisible against the backdrop of space. But we've gotten clever at detecting their presence indirectly by observing how they affect their surroundings.
So like if a star is acting a little funky, orbiting around something we can't see, that's a clue.
Exactly. Remember that bowling ball analogy? Even if you can't see the bowling ball itself, you can tell it's there by how it distorts the trampoline. Similarly, astronomers can infer the presence of a black hole by observing stars orbiting an unseen massive object. The stars move in these incredibly fast, tight orbits, a dead giveaway that something massive and invisible is holding them in its gravitational grip.
That's incredible. It's like cosmic detective work, using the laws of physics to track down these invisible behemoths.
And it gets even cooler. Remember when we talked about the Event Horizon Telescope, the EHT? That project gave us a glimpse of a black hole shadow, the closest we've come to actually seeing one of these objects.
That was huge. Seeing that blurry orange donut-shaped image was like looking into the eye of the cosmic storm. But how do you even take a picture of something that doesn't emit light?
That's the ingenious part. The EHT isn't capturing light from the black hole itself, but rather the light that's being bent around it. Imagine the black hole casting a silhouette against the backdrop of superheated gas and dust swirling around it. That silhouette, that shadow, is what the EHT captured.
That's mind-boggling. It's like taking a picture of a shadow puppet, but instead of a hand casting the shadow, it's a black hole warping the very fabric of space-time.
It's a testament to human ingenuity how we can use these incredible tools and techniques to study objects so far away, so extreme, that they challenge our very understanding of the universe.
It's truly humbling and awe-inspiring. So we've covered a lot of ground here, from Einstein's groundbreaking theory to the mind-bending implications of Hawking radiation. What's the biggest takeaway, the thing you want our listener to remember from all of this?
I think the most important thing to remember is that black holes aren't just these distant, exotic objects. They're integral parts of our universe, shaping the evolution of galaxies, influencing the very fabric of space and time. They push us to the limits of our understanding, forcing us to ask big questions and expand our horizons of knowledge.
Beautifully said. It's a reminder that the universe is full of wonders, mysteries yet to be uncovered. So to our listener out there, keep exploring, keep questioning, and never stop looking up at the stars. There's a whole universe out there waiting to be discovered.